All right, so today I'm going to be going over lesson 6.2. It's going to be about graphing and finding the key features of some certain functions like the square function, the square root function, which is something like this. There's a little 2 here, but we don't always write it. And that's also the same thing as writing x to the 1/2, as we learned in the previous lesson, 6.1. And we're also going to be investigating the cube root function, which is with a little 3 at the index of the radical, and you could rewrite that with a little 1/3 as the exponent. So these are all things that we learned, and we're going to be graphing these things, trying to figure out where they come from, why they're important, and why we care about knowing what they are. So let's first investigate x squared. X squared is just a simple function. Hopefully it's a review about finding out what the values and what shape appears on a graph. So if we have f of x is equal to x squared, that means when we plug in -2, we're going to square it. So for example, it's going to be -2 squared, which is going to be a positive 4. -1 squared is a positive 1, and so on, 0, 1, and 4. And now that we have these points, we have 5 points, meaning we could graph it. So we have -2, 4. We plug that point in, -1, 1, 0, 0, 1, and then 4. We're able to just graph these points as such. So if you guys forget what the name of this is, it's okay, but it's a little U shape called a parabola. Okay, so we have the parabola. Now we could just label these key features very quickly. We could find where it touches the x-axis. So if I'm looking at the x-axis, it touches right here. If I'm looking at the y-axis also, it touches at that same spot, and it seems to have a common vertex there. So this point's gonna have a lot of key features. It's x-intercept, the y-intercept, and the vertex. Also, the minimum is going to be the lowest value, which is going to be at the vertex. So it's going to be y equals 0. Specifically y, because we care about how high it is, or how low it is in this case. And for the max, it goes up forever, meaning it's infinity. The max is infinite, meaning we have no max value, so none. Since it's infinity, we have no max value. So on. This is just a review about domain and range. So domain is x, range is y. When we think about x values, we think about how far it goes to the left and the right. So we have a slight angle here, meaning it's going to go to the left slightly forever, and similar to the other side, to the right forever. So in that case, we have negative infinity and infinity, and we're writing it in interval notation. So that means with the parentheses. And we put parentheses because we don't ever reach infinity. Infinity is something that can't be reached. Inequality, surprisingly, we're going to use inequality symbols to write it with the appropriate notation. So negative infinity is less than x is less than infinity. It can't be less than or equal to. We don't include that little line under the inequality. Finally, we do x such that x is a part of all real numbers. This is kind of like the weirder one that you kind of have to just remember the form of it. But it's basically saying x is a set. That's what those little brackets are there for. It's a set. A set. The little line right here means such that. So I'm going to just write a little bit small. Such that, and then this other part is just saying x can be any real number. Right here. That's what that means. Okay, looks like we understand that. Now we're thinking about the lowest and the highest value. So the lowest value is going to be at the vertex, which is 0, the minimum, and the highest is going to go up to infinity. Being careful to note that it has a little bracket at 0, because we're touching 0. Furthermore, we can continue and say that y only has to be equal or bigger than 0 for it to be a part of the range. Very similarly, we say that y is set such that y is a part of our real numbers, and it has to be bigger or equal to 0 Okay, so that looks pretty good. And hopefully this is just review. But we need to think about how that function connects to the one that we are trying to investigate. And so let's take a little x squared function, for example. Now, if I were to ask what the opposite of x squared is, that would mean a square root. And we learned that in the notes yesterday, this would just equal x, meaning they're inverses. And if we remember what inverse functions are from Unit 1, we could remember that they are functions that have the x and y values switched. Now, okay, we're switching the x and y values, which is fine, but how does this make sense with our table, with our graph? So that means we're going to get these values right here, and we're going to switch them. So whatever was x, now is y. Whatever is y, now, whatever was y, now is x. So I'm going to start with the y's to x's. And now I'm going to start with my x, or I'm going to continue with my x's. -2, -1, 0, 1, 2. We're going to continue with this. See what kind of shape happens once we start putting in these points. We seem to get a very similar shape to what we did before. Only difference now is it's sideways. It's still a parabola, but it's a sideways parabola. And we did that by plotting the inverse points that we got by switching the x and y values. You'll see that we have a lot of the same key features. We still have a vertex at 0, 0. And now for our min and max, it still goes down forever and it still goes up forever. Even though it might be a little less obvious, you can see that there's a slight slope down here. So it goes down forever and then up forever, meaning there is no min or max. Okay, so if it goes down forever and up forever, then it's easy to write the range as such. So we're just going to write down forever, which is -infinity, up forever, which is +infinity. And I feel like it's easier to start with the range since we just talked about the min and max. We can write this like this. And then we're also going to write the set notation, which is y, such that y is a part of all real numbers. And when you do this, we also, okay, so we finish up with the range, and we're going to make some conclusions about this later. And now we're thinking about the domain. Domain is how far it goes left, which right here we have a point in the middle at 0. And it goes all the way to the right, which is infinity. Inequality, we just have to write x has to be either equal to 0 or bigger than 0. Finally, we have x is a part of all real numbers. Now, if you notice, when we switched the x and y, we also switched the domain and range. If you compare the domain and range of the other one, the function previous, it's exactly the same. Whoops, I forgot this one little part at the very end of the set notation for the domain. It has to be x is bigger than 0, like that. And I also did it for this bottom part right here. But anyways, you notice that the domain and the range are exactly the same, but just flipped. Whatever was the domain before, which was all real numbers, now that's the range, like this. Putting little stars to connect them. Now before, we had a range, and now it's the domain. And that seems normal. Or that seems to follow with the logic of inverse functions. And now here, we are very, very close to being able to say that this is an inverse function. So we flip the points, inverse, check, but now is it a function? And that I am not so sure about, because functions cannot have more than 1 point per every x value. And what I mean by that is if we were to do a vertical line test through each of these points, then we would see that it fails the vertical line test. And that means it's not a function. So it's not possible for us to call this an inverse function because it's not a function. It can't be an inverse function if it's not even a function. So therefore, we need to fix some part of this graph so that we can call this an inverse function. And what we're going to do is we're going to get rid of this bottom part now. So if we remove that bottom part, now for sure we could say it is a function. Look at that. Only passes through 1 point. So that is the concepts that I need you guys to understand. Since it wasn't a function, not a function, because of the vertical line test, it failed. We ignore the bottom. We get rid of the bottom. I'm going to say get rid of bottom values. And that's so that we have the definition of a function followed. If we were to say that it was an inverse function, that means we are not being consistent with the definition. We have to. And after this adjustment, we say that it officially is the inverse of the quadratic. The square root is the inverse of the quadratic function. So now that we understand what we're doing, let's see how it works whenever we try to do this for a different type of function, a cubic function. Now, reminder, cubic, the reason why it's called cubic is because we're involving ourselves with the 3D space, three-dimensional space, and cubes are easily expressed in the 3D space. So now we got this -2, and we're going to multiply it by itself 3 times. So -2 times -2, well, that's 4. And times another -2, it's going to be -8. 4 times -2 is going to be -8. So the negative stays there, but the value is just raised to the power of 3. So -1 cubed is going to be -1. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. 2 times 2 times 2 is 8. Now we got another set of points that we need to plot to see how it looks like. Let's check it out. So it might be kind of confusing to see what exactly is going on, but we're going to get something like this. So x-intercept, we got 0, 0. Y-intercept, we got 0, 0. Vertex, I don't like the word vertex because usually we use it in terms of minimums or maximums. So I like the word inflection point a lot more, which I'll say 0, 0. We see that it changes form in the middle, 0, 0. And then finally we have a minimum and a maximum. Well, it goes down forever, so there's none for minimum and there's no maximum. And if it goes down forever and it goes up forever, and if it looks like it goes to the left forever and to the right forever, then we could say it's all real numbers. So it's unbounded in every single direction, meaning we don't have to put any type of restriction on the domain and range. We just have to write infinities all across the board, making sure to write negative to positive, the least infinity to the greatest infinity. Finally, we do the set notation. X is a part of our real numbers. Then we do y is such that part of our real numbers. And that's about the extent of the cubic function. It looks like a nice, smooth curve with an inflection point rather than a vertex. And now that we have that, let's check out the cube root function. So we have similar motivations. If we have, let's say, x cubed, and we want to figure out an inverse operation, that means we need to cube root it. If you remember 6.1, that means that this 3 comes under, gives us 3 divided by 3, and that cancels out, so we're just left with x. So that is an inverse operation. So we're going to try to plot the inverse function by switching the x and the y values around. So I'm looking at these values right here. If before there were -8, -1, 0, 1, 8 as y's, now it's going to be -1 or -8, -1, 0, 1, 8 as x's. Same thing for the x's. If it was -2, -1, 0, 1, 2 as x's, now they're going to be the y's. We got some points. We can just plot them. We'll see how they look like. Oops, not there. -2, or -8, 2. we got negative 1 comma 1, 0 comma 0, 1 comma 1, 8 comma 2. And again, we end up with a smooth curve as our inverse. So we'll label our key features. Seems like a trend that we're getting the very basic key features down, just so we understand what they are. Again, I don't like the word vertex. I prefer the word inflection point. Okay, so our minimum, it goes down forever at a slight angle, so we don't have any minimum, and it also goes up forever. So since it goes down forever and up forever, and to the left forever and to the right forever, that means we're just going to do infinities all across the board. Our domain is not bounded by anything, and neither is our range. Finishing off with a set notation. Y such that y is a part of all real numbers. And the last question, is it an inverse function? Well, it is an inverse because we just switched the values. And is it a function? Does it pass the vertical line test? Looks like it does. Everywhere it passes the vertical line test. So we don't have to make any type of adjustment. We can, in full confidence, say that this is an inverse function because it follows both definitions of an inverse and a function. Now, the most important thing about this is being able to understand how we were able to get this type of function based on where we started with. So we started with an x squared here. We were able to change that or inverse it with a square root. That's where the importance of that function comes from. Similarly, we had x cubed, and we needed to figure out the inverse of that, which was x cube root. Few little points that I want you guys to remember is the symmetry that inverses need to have. So whenever we're plotting inverses with their original functions, then it is important to note down the symmetry that they possess between the original function and the inverse. Between this line is going to be called y equals x. And if I sketch a little rough drawing of the original function, we can see that the inverse kind of got rotated 90 degrees to the right. And that is the type of reflection that happens across that y equals x line. If we pretend that this graph is like a piece of paper, and if we try to fold it along that line, we would see that the graphs completely overlap on each other. Of course, this is without the adjustment that is necessary for the inverse function, but nevertheless, you see the symmetry. Same can be said about this inverse function right here for the cubic. It is symmetrical about this line. Going down the middle, which is y equals x. It's a linear function. Get rid of these vertical line tests for a second. And if I do a little sketch, you're going to see that it goes something like this. That line might be a little too steep, but it's okay. It's just a sketch. So it does have symmetry still. And that is the graphical element that I want you to see with inverses. Now again, just to reiterate, just to close this lesson, it is very important to understand where these functions come from. In algebra, we concern ourselves a lot with being able to come back from where we started. So if we add 5 to one side, we also have to add it to the other. And then if we subtract it to both sides, we can subtract 5 to both sides to get where we started with. If we need to solve for x, how many times have you guys needed to multiply both sides by a number, or divide both sides by a number, or add or divide, or add or subtract? It's going to be the exact same case with these square roots. That concludes this lesson. We're going to continue with 6.3.